Hey there, Chemistry 3111. We're going to start off today with section 22.10. And we just finished the Hoffman elimination section. So now we're moving on. We only have a few sections left in this chapter. And you probably noticed right away that it says 22.10 deals with the reactions of amines. So amines, and I just put a primary amine for the heck of it, okay? But when it says amines, it means primary and secondary in this section. So primary and secondary amines with nitrous acid. So what's the formula of nitrous acid? It's HNO2. So you probably remember nitric acid. So HNO3, that's nitric acid, which is one of the strong acids. And then if we remove an oxygen from it, we get HNO2. And again, HNO2, that's nitrous acid. And the reason we don't talk about nitrous acid that much is because in General Chemistry 1, we're mostly dealing with strong acids. And there's various and sundry reasons why nitrous acid doesn't show up a lot in Gen Chem 2. But the main one is that it's not stable. Okay, it's not a stable compound. And so what we do is we actually make nitrous acid in situ. So what does in situ mean? In situ means in place. So if we write here, in situ means in place. So that means it's made in a reaction flask, in place. So how do we make nitrous acid? Because if you've studied the slides at all, you'll see that nitrous acid is right here. This is the Lewis structure of HNO2. So here's nitrous acid. And it's actually made from a mixture of sodium nitrate, NaNO2, and HCl. So you mix those two together, you get a proton transfer to make nitrous acid, then you get another proton transfer by HCl to make water as a leaving group, and then you form this interesting ion that's shown down here on the bottom right-hand side called the nitrosonium ion. You have to know the nitrosonium ion, not to be confused with the nitronium ion. So back in chapter 18, we looked at the nitronium ion. I'm just writing this down here so you don't get the two of them mixed up. But the nitronium ion was this, okay? And that was to make a nitro group on an aromatic ring. So again, this was covered in chapter 18. I just don't want you to confuse those two things. But the nitrosonium ion, it consists of only one nitrogen and one oxygen. You can see it must be electrophilic because it's got a positive charge. We have two resonance contributors. In the second one here, you can see that everybody has a complete octet like that. So the nitrosonium ion, again, is produced in situ by a mixture of nitric acid and HCl. So we form nitrous acid, it gets protonated, again, loses water, and we make the nitrosonium ion. So what we're interested in is what's going to happen when we make that nitrosonium ion. It's very electrophilic, but how is it going to react with an amine? Well, again, what we're going to see in this section is that it will react with primary amines and it will react with secondary amines, but the nitrosonium ion will not react with tertiary amines. So let's get into it here. And we actually start with secondary amines, and there's a good reason for it. You'll understand why when we look at the mechanism. So reaction of a secondary amine with nitrous acid, which again, the nitrous acid is formed from a mixture of sodium nitrate and HCl to make the nitrosonium ion. And that nitrosonium ion reacts with the nitrogen. We have a lone pair on the nitrogen. And you can see the mechanism right here. You form the nitrosonium ion. So here's the nitrosonium. And then your secondary amine does a nucleophilic attack. You end up doing a proton transfer, and you end up with a new brand new functional group, and that is what we call an N-nitrosamine. So that's this guy right here. Pretty neat looking compound here. So an N-nitrosamine is what we get from a secondary amine. So let's write that down just to be sure. Secondary amine and nitrous acid. Again, you never write HNO2 over an arrow. You put sodium nitrate and HCl, and you form the nitrous acid in situ. And then it forms the nitrosonium ion. So, if you're probably sitting there, you're looking at this and going, okay, well, that's great. What's the synthetic utility of the N-nitrosamine? Well, it turns out there isn't a whole lot of use for us as Chemistry 3111 students in an N-nitrosamine. In fact, they're potent carcinogens, and you should know that something that is carcinogenic is something that is known to cause cancer. And you can see all these N-nitrosamines, The first one here is N-nitrosodimethylamine. This is a derivative of dimethylamine, obviously. That's found in things like cured meats and beer. That's found in beer. So that's a potent carcinogen. It's also, you see this N-nitrosopyridine, which is found in bacon. And then, of course, you've got this derivative of nicotine here, which is found in tobacco smoke, okay? So N-nitrosamine is not a good thing, okay? We generally don't say yay for N-nitrosamines. Anyhow, there we go. And if you're wondering, where does this come from in fish? Well, it actually comes from the dimethylamine that's found in fish. So if you have a fish like herring or something, right, which is consumed on a massive scale, not so much in America, but in Europe it sure is. And then they mix it with sodium nitrite, which is a preservative, and then they end up forming, N-nitrosamines from it, or this N-nitrosodimethylamine. And that can actually cause liver cancer in farm animals because they use the herring as fish meal, and animals consume that. Anyhow, that's a whole other kettle of fish, no pun intended. So I'm not going to spend too much time on that. But anyhow, this is going to be of more interest to us. It's going to be the reaction of a primary amine, okay, with a diazonium salt. And when we do this, a primary amine with nitrous acid, and we make a diazonium salt. So this is a new functional group, the diazonium salt. You can see that it's a salt because we have a cation and an anion. And so, Maria, it's more complicated than that. I'll try to explain it during the break. All right. So anyhow, if you take a primary amine and you treat it with nitrous acid, okay, which does the diazotization reaction, you form a diazonium salt. And we call this process diazotization, and it does have synthetic utility. Okay, so let me explain what the synthetic utility is in just a sec. But the reason why we do secondary amines first and primary amines last is that you probably notice, if you look at this mechanism, that you recognize this first part all the way to here, essentially, all the way right to here. You form an N-nitrosamine, and then you have a series of proton transfers and a loss of water to make the diazonium salt at the very end. So the first part is something that we saw when we did the secondary amines, but now with the primary amine, we do 1, 2, 3 proton transfers, loss of water, and we end up with a diazonium salt. So what can you do with a diazonium salt? Great question. The first one is, if you have an alkyl diazonium salt, those are actually really unstable, and they can explode, and they usually rearrange anyway to give you a whole variety of products. So that would be if you had some kind of just generic R group and then a diazonium, which we can usually just write like this, okay? These are explosive, okay? Let's see here, explosive, so, not very useful when R is an alkyl group. Okay, so what's the what kind of group would we have if we didn't have an alkyl group? Well, we could have an aryl group. Okay, so when we have an aryl group, it turns out that an aryl diazonium salt is more stable, and it's got a lot of synthetic utility, a heck of a lot of it. Now, usually we write our diazonium salts. You can write it like this. You could abbreviate this as this. That I would be totally okay with that as well. But you should, I think it's a good idea to include the chloride here anyhow. And then you can do a bunch of different reactions here. You can do what's called Sandmeyer chemistry, the Scheemann reaction, and a couple of others, and you can add new functional groups to an aromatic ring. So this is almost like a continuation of chapter 18 in a way. Okay, it's not exactly the same thing because it's not electrophilic aromatic substitution, and it's not an SNAR, it's diazotization. So that's why it's in chapter 22, because we use an aniline derivative. But it's still kind of in the same vein because we're putting new groups on an aromatic ring. So let's take a look. And the first one that I've mentioned before the break even started is the Sandmeyer reaction. And there are several iterations of the Sandmeyer reactions. And basically all we do is we take our diazonium salt, okay, and we treat it with copper 1 bromide, copper 1 chloride, copper 1 iodide, or copper 1 cyanide. And that way we can incorporate a bromide, chloride, iodide, or cyanide, or sorry, a nitrile, I should say, into the molecule. Okay, there's no mechanism for any of this in the textbook, so it's just kind of a reaction that you need to know, and that's all there is to it. It's nothing more than that. one of the neatest things about the chemistry that's on this page in particular is if you form benzonitrile, this compound in the bottom left, you know that we can take that and treat it with acid and heat it up, and that from that we can make benzoic acid. So it gives you a new way to put a carboxyl group to make a carboxylic acid on an aromatic ring. And that's what they're trying to show you in this slide here, okay? So now we're switching gears from 20.10 to 20.11 and continuing on with this whole idea of aryl diazoniums. And so it says here that overall the Sandmeyer reaction is part of a whole multi-step sequence to install a carboxyl. So remember, this is called a carboxyl group on a benzene ring. So if we have cumene, that's this molecule here, right? Cumene, there we go. What's happening in the first step is we're nitrating, right? So we add a nitro group, then we reduce it with iron, then we neutralize with base, and then we do the diazotization reaction, right? We treat it with nitrous acid, which is formed by sodium nitrite mixed with hydrochloric acid, and that makes our diazonium salt. So diazonium salt. And of course, this is an aryl diazonium salt. And then we can do a Sandmeyer reaction. So this is Sandmeyer, right? We treat it with copper 1 cyanide. Remember, copper 1 is the same thing as cuprous. So cuprous, so you could call it cuprous cyanide as well. And then we can hydrolyze that nitrile from benzonitrile to give us this carboxylic acid. This, what would you call this? Para-isopropyl benzoic acid. All right, so a new way to install a carboxylic acid. There's some other ones here that I can't give you any more information other than memorize it, really. And that's because our book doesn't go into any detail about these reactions whatsoever. This one here, this first reaction, this is called the CHEM reaction. I think the name is in the textbook. So the CHEM reaction, and it uses fluoroboric acid. So this is called fluoroboric acid. So fluoroboric acid with your diazonium salt, and that will install a fluorine. And if you think about it, we've never talked about any way to install a fluorine on an aromatic ring. In fact, it can be challenging to do that. So using Sandmeyer chemistry, this is a variation of it, the CHEM reaction, I guess. And we make an aryl fluoride. So this would be fluorobenzene, of course. And then you can also just treat it with water and heat it up, and that will make phenol. And if you think about it, we don't have a lot of ways to make phenol derivatives, right? Not many ways to make phenols whatsoever. And so there you go. There's a way to make a phenol now. And again, there's no mechanistic details for these reactions whatsoever in the class. So I just want to practice a little nomenclature with you here for a sec before we go to the next slide. If I was to write down this acid here, H3PO4, does anybody remember what the name of this acid is? Yeah, thanks, Audrey. It's phosphoric acid, so phosphoric acid. Yeah, so if we have H3PO3, then it becomes phosphorus acid, right? So phosphorus acid, just like we went from nitric to nitrous, we go from phosphoric to phosphorus. And then what if we had H3PO2? Well, maybe you don't remember this, maybe you do, but this one you would call it hypophosphorus acid. Hypophosphorus acid. All right, and I just want to practice that with you because some of my students are interested in taking MCAT and things like that, and they do ask nomenclature questions. And so in this slide, we're actually going to use hypophosphorus acid, which we just reviewed the nomenclature, where that name comes from. And if you take your diazonium salt and you treat it with hypophosphorus acid, it just replaces the diazonium with a proton. And if you're thinking, what's the utility of that? Well, check this out. This is where you would use this. Now, this you kind of have to remember a little bit of chapter 18, chemistry. Okay, you have to think about chapter 18 a little bit. Do you remember that we talked about this reaction here? We said if you take aniline and you treat it with bromine, it's so activated because you have electron density that can be donated into the group, into the aromatic ring here by resonance, that this thing will just polyhalogenate. Well, it actually has some synthetic utility, this reaction. okay? And the synthetic utility is really based on this molecule here. So we would call this 1,3,5 tribromobenzene. And based on everything that I've taught you until this point, we have no way to make this molecule whatsoever, okay? We don't know any way to do it. But now, based on on this reaction with hypophosphorus acid, we can do it. So the idea is this, and it's kind of a very specific synthesis that the book is interested in. But the notes that I have in front of me, what I wrote down is that this compound that I have in the green circle, it's actually difficult to make otherwise. And the reason why, another reason, is that bromine, think about it, bromine is an ortho para director, and everything here is meta, right? They're all meta to each other. So that's another reason why it's difficult to make this compound. So here's the scheme, okay? You're going to take benzene, you're going to nitrate it, then you're going to reduce it, neutralize it, and that makes aniline, okay? Then you do this polyhalogenation, right? Because this is such a activating group. So you end up with all of these bromines on it, and then you make the diazo compound. So this is your diazotization, and then you treat it with hypophosphorus acid, and that replaces the diazonium for a proton. Again, it's a very specific synthesis, but it is in the textbook. Therefore, I think it's important. So I do want you to know it, and it could come up in homework and things like that. So just to put that bug in your ear, and I know you're all very astute students. So there you go. All right, so I believe this is the last reaction of the entire chapter, which is azo coupling. And I think that this comes up in another chapter as well, the idea of azo coupling. If you pay attention to the introduction of the chapters, there's one chapter where it talks about fruity pebbles. And where do the bright colors come from? And fruity pebbles. I have some fruity pebbles upstairs in the pantry, right? I got 3 kids. You got to have fruity pebbles around. So those colors of the fruity pebbles actually come from diazo compounds, like this one here. I don't know if it's this one specifically, but these kinds of compounds where you have sort of this portion here, where you have 2 aromatic rings, and then we call this the diazo unit here. You can put various substituents on the aromatic rings, and it makes all kinds of different colors, okay? And so the way that we make these compounds is through a process called azo coupling. And really, the questions that we ask you about azo coupling, I don't want to say they're not difficult, because that's not a good thing to say to your students, but I would say as long as you understand activating group and deactivating group, from chapter 18, you should be pretty good on the azo coupling. So here's the expectation, right? So let's think about it. If you had an aryl diazonium salt, okay, this compound right here. So I'm just going to redraw the compound here, okay, and I'll draw the Lewis structure the same way they have it, like this. Okay, we have a positive charge here, and we have our chlorine. Okay, so let's just forget about the chloride for a second. Let's just think about the diazonium ion that I have here in the blue box. Is that going to be a nucleophile or an electrophile, what I have in the blue box? If it's got a positive charge, what will that be? Is it going to be a nucleus? It's going to be a big-time electrophile, isn't it, Audrey? Right, it's going to be a strong electrophile. So strong electrophile. So what does that mean? It means it's hungry for electrons. And so in order for it to react with another aromatic group, so, right, this part is going to come from your diazonium ion here. Well, the other part of the molecule, this part here, has to come from something that has an electron donating group on it. Now, on the hydroxyl, the oxygen is electron withdrawing through induction, but it's electron donating through resonance. So you've got to have an electron donating group on your nucleophile, okay? So this is our nucleophile. Okay, and it has to possess an electron donating group, and we do in phenol. So what happens is you get a nucleophilic attack by the aromatic ring on the diazonium ion, like you see here, and you end up with what? Hey, look at this. It's chapter 18 all over again. Who remembers the sigma complex, right? We talked about this 100 times in chapter 18, right? Exactly. Well, somebody says, woo, right? It came up so many times in chapter 18. And if you're wondering, is this the same sigma complex? Exactly. It's the exact same thing, okay? So we form our sigma complex. You can see all the resonance contributors here. And then what do we do at the end? We do a proton transfer with our chloride. We restore neutrality and we make our diazonium compound. So we call this a diazonium compound. And yeah, I even have written in my notes here, literally in my notes that I'm looking at, it says fruity and pebbles. Not petals, Mr. Dion, pebbles. There we go. Like one of my sons said the other day, because we had bought fruity pebbles, he said, pebbles, that doesn't sound very appetizing. Or something. Where did you learn the word appetizing? Anyhow, so azo coupling is used to produce azo dyes. Again, this is covered in chapter 18 a little bit. And they have all of these interesting colors like bright yellows and bright greens and bright blues. And if you're wondering, like, why do they have color? It's because they're highly conjugated. So you have double, single, double, single, double, single the whole way through. So all you have to do is vary the substitution. And if you're wondering, well, what kind of substitution? Well, the textbook has some examples. And we're going to do a practice problem where you see some different substituents. And it's the different substituents that make different colors, okay? And so if you look at a package of M&Ms, it'll say dye number 3 and dye number 6 or something like that. And so a lot of times those are diazo compounds. Anyhow, just kind of an interesting synthesis. Mr. Dion isn't big into synthesizing compounds that aren't drugs, but hey, whatever. Fruity Pebbles deserve some mention maybe in the class too. Anyhow, so with that wraps up all of the new chemistry in this chapter. There's nothing that we haven't covered in terms of reactions. There is a little section here on heterocycles, and then there's a little section on spectroscopy. But before and I'll mention those briefly, let's try synthesizing some of these compounds here. So we're going to take nitrobenzene, and then we're going to convert it to 1,3-dibromo benzene. I'm going to switch over to a blank document just so I have enough room to do it, the whole question here. So where was I? This is question chemistry 3111. Let's try. Do I have enough real estate in here? I only have some, not enough, but let's give it the old college try here. So this is question 22.26, and this is B. So we want to go from nitrobenzene, and we want to make 1,3-dibromobenzene, this compound right here. So what do we know about bromine? Is bromine a meta-director or an ortho-para-director? Anybody remember? It's a weak deactivator, I know that. Thanks, Audrey. Thanks, Deanna. Thanks, Sydney. All of you are 100% correct. So this is an ortho-para-director. And so we can't use bromine to direct anything. All right. What do we know about nitro, though? It's electron withdrawing, so it is a deactivator. But what kind of director is it? Heck yeah, it's a meta-director, right? So what we should try to do then is install the bromine first, right? Absolutely. So let's put a bromine in first. And since we're using a deactivating group, we're going to need a Lewis acid. So we'll use bromine, and we'll use iron 3 bromide. And we're going to end up with this compound here. It looks like this, okay? So now we need to convert the nitro to a bromine. And what are we going to do? We're going to use Sandmeyer chemistries, right? So to get from here to here, we're going to use Sandmeyer reaction. So the first thing we're going to do is we're going to make the diazonium salt. I'm going to write out both steps here. So we're going to put, let's see here. Oh, I need to reduce it to the amino group first. I forgot about that. So we'll reduce it. I'll just use iron and HCl and heat it up. I don't even know if you need heat to really do that. So then we'll use sodium hydroxide to neutralize. So we'll end up with the aniline derivative. So this will be 3-bromoaniline, like this. Let's see here, 3-bromoaniline. I'm going to try to write out all the intermediates. So now we're going to diazotize. And for that, we're going to need sodium nitrite and HCl. That's going to give us the diazonium ion. Diazonium salt, more correctly. So we write down the diazonium salt like this. And then we do the Sandmeyer reaction. So this is a Sandmeyer reaction. And for that, we just need copper, 1 bromide, or cuprous bromide. They both mean the exact same thing. So now we've taken nitrobenzene and we've converted it to 2,3 dibromobenzene. So that one didn't seem too bad. Let's try another one here. So this is going to be question C. And in this one, we're trying to take benzene and we're going to make a phenol derivative. So we're going to make a phenol derivative. And this is going to be metapropylphenol. So wow, we've got 2 ortho-para-directors here, right? An alkyl group is an ortho-para-director, as is a hydroxyl. Now the hydroxyl is a strong activator, and the alkyl group is a weak activator. But either way, they're both ortho-para-directing. But what we could do is we could make this compound from the amine, right? And that could come from the nitro. So what I'm saying is we could make it from this compound, or something like this maybe. And of course that we would get from the nitro, right? And we know that the nitro is an ortho-para-director, but we can't install a propyl group directly, can we? We know that that's going to undergo a carbocation rearrangement if we try to do a Friedel-Crafts alkylation, but we could do an acylation, right? And then burn off the carbonyl. We could do that using a Clemmensen reduction. All right, and this one's kind of an interesting one. I actually did look at the solutions manual for this, and the solutions manual made a note that I want to go over with you in just a second here. So when it comes to the acyl group, so if we wanted to make this compound that I'm putting in this black box, when it comes to the acyl group and the nitro, these are both meta-directors, right? This is a meta-director, and this is a meta-director. Which one of these do you think you should install first, though? Does anybody have a feeling about that? There's a right and yeah, it's the carbonyl, isn't it? Yeah, absolutely, because it's a weaker deactivator, right? Nitro is super deactivating, so we'll want to put that in last. So let's do our Friedel-Crafts acylation. Great. So for that, we're going to need propionyl chloride, and we're going to need a Lewis acid like aluminum chloride, and that's going to install our acyl group. So we'll put the acyl group. Oh boy, I'm running out of space already. Here we go. So we have our acyl group in there, and now we can do our nitration. So this takes just the old classic nitration conditions of nitric acid mixed with sulfuric acid, and that makes the nitrosonium ion, or sorry, the nitronium ion. I'm getting the two mixed up. The nitronium ion, and then we do our nitration reaction, which looks like, oops, looks like this. So we have our acyl group installed. Now we have our nitro group. And so this is where the solutions manual kind of showed me something, is that if you want to get rid of the carbonyl here, you can do a Clemmensen reduction. So if we do a Clemmensen reduction, which is zinc and mercury amalgam and HCl and heat, okay? This is, again, this is a Clemmensen reaction. This should reduce the nitro as well. So should reduce nitro also, right? Because we have a mixture of zinc and HCl. So yes, it should reduce the nitro. If you had done it in 2 steps, like first you did the Clemmensen and then you did a reduction with iron and HCl, I wouldn't care, okay? It's totally fine. But our textbook says, well, you can kind of do a double whammy in this case. So I'm just going to do it the way he does it in the textbook, and that is to reduce both. So now we have the propyl group installed and we have the amine. And now it's just a matter of doing our diazotization followed by treatment with water. So we're going to treat this with sodium nitrite and HCl. That makes our aryl diazonium. So we'll scribble that down. I'm going to write a condensed formula. So N2 with a positive charge like this. Then we have our propyl group. And then the last part is just to treat it with water. So all we do is treat it with water and cook it up a little bit. So we just boil that, and we end up making a phenol derivative. Give me a thumbs up if you follow me on that one. Everybody with me on that one? Cha? All right, all right. Well, let's try one more. Let's try, or one more from this question. This is 22.26D. Let's see here, 22.26, and this is D. And we're taking benzene, of course. Who would have thought? Starting with benzene, and we're trying to make para-tert-butyl-benzoic acid. So this molecule here, and I'm sure that you all have good ideas about how to make this molecule, because honestly, based off of all the things you've learned in this class, there's more than one way to make this molecule. Definitely more than one way. Okay, so just in the spirit of chapter 22, let's do it by a diazotization. So we'll do the Sandmeyer with cuprocyanide. So meaning if we do the Sandmeyer with first would be Cu, Cn, and then 2 would be just hydrolyze that in aqueous acid and heat it up. So that means that we would need to make this compound, we'd need to make this diazonium salt, like this. Okay, so now the question becomes, well, if we make that, then we have to make the amine, right? So we'd need to make this compound, right, like that. Okay, and based on those two, well, you've got to make the nitro compound as well. So if we do another, really getting carried away with the retrosynthesis today. But anyhow, it boils down to this compound here, doesn't it? So we have a tert-butyl and we have a nitro group. Can anybody tell me which one of those groups should I install first? Would it be the tert-butyl or the, yeah, okay, I knew you'd know the answer, right? Because the tert-butyl, right, Audrey, it's ortho-para-directing. And it's definitely going to direct preferentially to the para side, isn't it? And nitro is meta-directing. Good. So let's install that tert-butyl group, and we need to do Friedel-Crafts alkylation for that. So for that, we're going to use tert-butyl chloride and aluminum chloride, and that's going to install our tert-butyl group. So the rest of it is just kind of putting steps together that you know. The next part is going to be the nitration. So we're going to use nitric acid. There we go. And sulfuric acid, all mixed up together like so. Sorry, my drawing skills aren't on point today. Anyhow, then we need to do the reduction. So again, we learned a few ways of doing that, but the easiest way is just use iron, metal, and aqueous acid and cook it up. This is a reaction I did many, many times. I worked in HIV for a long time. And this is a reaction we used to do all the time. Let's see, so we end up with our amine, then we diazotize. So we're going to treat it with sodium nitrite and HCl. We make our diazonium ion. Luckily, aryl diazoniums are not explosive, so that's good, unlike an alkyl diazonium, which is explosive. And so for the last part, we're going to first treat it with copper cyanide to make benzonitrile. So this is our Sandmeyer reaction, Sandmeyer. And then in the second step, we're going to just hydrolyze the nitrile to a carboxyl group using aqueous acid and heat. All right. Now, I would say there's a completely different way of doing this reaction. Okay, there's nothing wrong with this. Give me a thumbs up if you follow me on this, or stop me if you have a question. Everybody okay with this one? Because I would say there's another way, right? There's certainly another way to do that, and that would be to start with the tert-butyl benzene, right? And would be to brominate that. So just use bromine and iron 3 bromide, and that would make the para-tert-butyl bromobenzene, this compound here. And then you could treat it with magnesium, followed by solid CO2, followed by aqueous acid, right? So you could do some Grignard chemistry, and that would convert the bromide into the carboxylic acid. Okay, like that. There's nothing wrong with either of those routes. It's just, you do have to know the Sandmeyer chemistry, so they wanted us to practice that in here. Let's try question 22.27, so just bear with me as I go back to the slides here. And of course, it's way down at the bottom. So let's see, I think it's up here somewhere. Where is it? This question here, 22.27. So it says, identify the reactants you would use to prepare the following compound with an azo coupling reaction. So I'm going to show you what we would expect for you as Chemistry 3111 students. So look, the first thing you do is this. You look at all the substituents. So we have a sulfonic acid here, a sulfonic acid here. These are both electron withdrawing groups, right? And so these are deactivating, okay? Therefore, deactivating. Now, if we have an amino group, that is an electron donating group via resonance, and therefore it is an activator, okay? It's actually a strong activator, but anyhow, it's the only thing on here that's an activator. So the part that has the activator on it, this is going to be your nucleophile, all right? And the part with the electron withdrawing groups, that's going to be the part that makes your electrophile. So electrophile, okay? That's going to make your electrophile. So if you want to draw the electrophile, it's going to look like this. So we're going to have our sulfonic acids. And then you've got the diazonium ion, right? Because that's the electrophilic, right? If it's got a positive charge, it's an electrophile. And your nucleophile is going to be the aniline. So this compound here. All right, that's going to be your nucleophile. So if you're wondering, like, what does the textbook expect of me with respect to this, or what does the homework expect of me? All they expect you to be able to do is this, is to say, okay, this is going to be my reactant, okay? So copy, and I'm going to paste this over here. Okay, but now I'm going to change the color of it to red, because what the textbook always wants you to do is to write down the steps of the diazotization. So they want you to start with the aniline and say, okay, I'm going to diazotize that with sodium nitrite and HCl, right? That makes the diazonium salt. And then all I have to do is throw in the nucleophile. So I put in my aniline, right? And that's my nucleophile. And that's going to give me the product. And that's all you need to know. Okay, as a Chemistry 3111 student, you're going to have to go over the practice problems in the textbook, but I think this is about the level that we go to in this class with respect to diazotization. All right, nothing more than that. The section on nitrogen heterocycles, now it says to skip it, and that's because we don't ask any of the heterocycle chemistry, but you should be aware of a heterocycle. A heterocycle is any kind of cyclic compound that contains any atom other than carbon, really. So most heterocycles have nitrogen, oxygen, or sulfur in them. And you can see if you look at the list of, the top 200 marketed compounds that I think I posted in an announcement, most of the prescription medications out there, the vast majority of them have heterocycles in them. And you can see whether it's Nexium or Viagra, right? They both have several heterocycles in them. And you probably recognize a pyrimidine, right? There's a proportion of a pyrimidine here. If you studied biology at all and you've studied DNA and RNA, you've probably learned the purines and the pyrimidines. And here we have a pyridine. This one here, this is called a, you've got morpholine, piperidine. This is called piperazine is the name of this ring here. So anyhow, the idea is that, heterocycles are everywhere, okay? And so in order to become a real expert in medicines, you have to know a lot about heterocyclic chemistry, but that would be a whole other class in organic chemistry. Anyhow, and the part about spectroscopy, we could leave this as an FYI because you've already studied IR in Organic 1 and you would have studied it in the lab as well. But just to review a little bit of it, right? You should remember that when you have a primary amine, right? A primary amine gives 2 stretches. And it's not because of, the 2 protons. If you had me as an instructor, I'm not going to act it out for you ever again. But I probably explained to you the difference between symmetric and asymmetric stretching with my arms, which I usually acted out in class. And then if you have a secondary amine, well, a secondary amine only has 1 NH bond. And so we only see one IR signal for the NH stretch. And then tertiary amines, of course, they don't produce anything in the IR for NH stretches because they don't have any hydrogens on the nitrogens. All right, what else? Nitrogen, hydrogen bonds. So what about the H protons that are, the H's or protons that are bound to nitrogen in the NMR? They usually come out between 0.5 and 5.0 parts per million. So it's quite a large range. And if you're like, why is the range so big? It's because there's a whole bunch of things that can affect the chemical shift. Okay, the chemical shift is affected by concentration, the solvent, the temperature. It's all, these things affect the chemical shift big time. And so we can actually remove the nitrogen, the hydrogen bound to the nitrogen. We can get rid of that signal in the NMR by putting it in D2O. So all you do is you shake the sample in deuterium oxide, so D2O instead of H2O, and it replaces the hydrogens with deuteriums, and then you can't see them. Anyhow, it's an experiment that I don't think we talk about much in the lab or even in this class. And then lastly, or I think it's, lastly for NMR, is you should remember that nitrogen is actually quite an electronegative element. So it has an electron withdrawing effect that you see here on these methylenes, right? We talked about the baseline of a methylene being about 1.2 parts per million. So you can see it has an electron withdrawing effect of about 1.5 parts per million. And the alpha position, it drops off in the beta and in the gamma, there's no effect. Carbon atoms that are bound to nitrogen, those usually come out around 30 to 50 parts per million. And again, it's because nitrogen is electron withdrawing, right? It is quite an electronegative element. And then spectroscopy, if you had me as your instructor or Mr. Geiger, I'm sure that both of us covered alpha cleavage with you in detail. So you should be aware of that, especially if you're taking the lab right now. I'm sure that Mr. Geiger would ask you about alpha cleavage. And of course, we cover that in Organic Chemistry 1. So by way of a review of all the reactions in this chapter, you'll notice that the first couple review reactions here are actually things that we studied before, right? We talked about the SN2 of a primary alkyl halide with sodium cyanide, right? You have the cyanide ion like this. It does a nucleophilic attack. You get a loss of leaving group. Then you make a nitrile. Right? This is called a nitrile. And then you reduce the nitrile to an amine. So you make an amine from the nitrile. If you have a carboxylic acid, you can treat that with thionyl chloride. That will make the acid chloride. Then you treat that with ammonia in excess. That will make an amide, and you can reduce the amide with lithium aluminum hydride again. To make an amine from benzene, so to make some kind of aniline derivative, well, how do we do that? We make it from a nitro compound. And you can either hydrogenate it, as is shown here, or you see that we have a whole holy host of different reducing agents. You've got iron, zinc, tin, and acid. All of those will work. And the tin 2 chloride, the reason why we cover this one in this chapter is this is a mild reducing agent. And you can reduce a nitro in the presence of other functional groups. And then, of course, all of those would give you an aniline ion, so you have to treat it with base, and that eliminates the aniline ion. After that, we talked about azide synthesis. So we said you can take sodium azide, and we went over the Lewis structure of azide, which looks like this. So we went over the whole Lewis structure of azide and talked about how azide is a nucleophile. So you get nucleophilic attack, loss of leaving group, then you form an alkyl azide, and you could reduce that via hydrogenation or lithium aluminum hydride reduction. Then we went over the Gabriel synthesis, which is really an improvement over the azide synthesis because they can, be highly reactive. So you use phthalimide, and you treat that with potassium hydroxide. That does an SN2. And then you treat that with hydrazine. So this is hydrazine. And that's really the best way to make the amine, because if you hydrolyze it in acid, then you have to do a second step, which is basify. Then we talked about reductive amination, one of my reactions that's near and dear to my heart, which uses sodium cyanoborohydride. So we use a catalytic amount of acid, an amine of some sort, okay, ammonia, primary or secondary amine, and then we use sodium cyanoborohydride, this new reagent that we learned. And we said, well, this is a less reactive version of sodium borohydride. So what we actually do is we form an iminium ion. Okay, so we form an imine in situ, and then that ends up getting reduced, right, using the sodium cyanoborohydride. Then we talked about acylation as a protecting group. So this is a protecting group. And when we would use that, and so we went over all the reasons why we would use that, Today we did reactions with nitrous acid, and we said that we could use the diazonium salt to do Sandmeyer chemistry and some other reactions like the CHEM reaction. Then we looked at Hofmann elimination. This goes all the way back to chapter 7. Really was the time when you would have been introduced to the word Hofmann, that name, and what it's used for. So it's not really a new concept, but the reaction conditions are new with an amine, right? Because we don't think of an amine as a good leaving group, but you do an exhaustive alkylation, right? You add 3 alkyl groups, it has a positive charge. Then you do an elimination reaction using a silver oxide, and you heat that up in water. Then we talked about all the Sandmeyer reactions that you need to know with cuprous bromide, chloride, iodide, and cuprous cyanide. Then we went over the CHEM reaction. I guess the name is in here. So that's fluoroboric acid that you use to install a fluorine. We talked about reaction with water and heat. That makes a phenol. And then hypophosphorus acid just removes the diazonium ion and installs a proton in that position. And then the last thing we looked at, the very last thing, is the azo coupling. So remember that on your nucleophile, you want to have an activating group, right? Some kind of electron donating group. So if you have to review your chapter 18 chemistry to make sure that you understand all that really well, there's no shame in that. I would totally do that. All right. And that covers the entire chapter.